1. The origin of life, from out the turning globe. Night followed day in swift succession. On Earth, at that time, a day lasted for only 5 or 6 hours. The planet spun madly on its axis. The moon hung heavy and threatening in the sky, far closer and so looking much bigger than today. Stars rarely shone, for the atmosphere was full of smog and dust, but spectacular shooting stars regularly threaded the night sky. The sun, when it could be seen at all through the dull red smog, was watery and weak, lacking the vigor of its prime. Humans could not survive here. Our eyes would not bulge and burst as they may on Mars, but our lungs could find no breath of oxygen. We'd fight for a desperate minute and asphyxiate. The Earth was named badly. Sea would have been better. Even today, oceans cover 2/3 of our planet, dominating views from space. Back then, the Earth was virtually all water, with a few small volcanic islands poking through the turbulent waves. In thrall to that looming moon, the tides were colossal, ranging perhaps hundreds of feet. Impacts of asteroids and comets were less common than they had been earlier, when the largest of them flung off the moon. But even in this period of relative tranquility, the oceans regularly boiled and churned. From underneath, too, they seethed. The crust was riddled with cracks, magma welled and coiled, and volcanoes made the underworld a constant presence. It was a world out of equilibrium, a world of restless activity, a feverish infant of a planet. It was a world on which life emerged 3,800 million years ago, perhaps animated by something of the restlessness of the planet itself. We know because a few grains of rock from that bygone age have survived the restless eons to this very day. Inside them are trapped the tiniest specks of carbon, which bear in their atomic composition the nearly unmistakable imprint of life itself. If that seems a flimsy pretext for a monumental claim, perhaps it is. There isn't a full consensus among experts, but strip away a few more skins from the onion of time, and by 3,400 million years ago the signs of life are unequivocal. The world was heaving with bacteria then, bacteria that left their mark not just in carbon signatures, but in microfossils of many diverse forms, and in those domed cathedrals of bacterial life, the meter-high stromatolites. Bacteria dominated our planet for another 2,500 million years before the first truly complex organisms appeared in the fossil record. And some say they still do, for the gloss of plants and animals doesn't match the bacteria for biomass. What was it about the early Earth that first breathed life into inorganic elements? Are we unique, or exceedingly rare, or was our planet but one in 1,000,000 billion hatcheries scattered across the universe? According to the anthropic principle, it scarcely matters. If the probability of life in the universe is 1 in 1,000,000 billion, then in 1,000,000 billion planets there is a chance of exactly one that life should emerge somewhere. And because we find ourselves on a living planet, obviously we must live on that one. However exceedingly rare life might be, in an infinite universe there is always a probability of life emerging on one planet, and we must live on that planet. If you find overly clever statistics unsatisfying, as I do, here is another unsatisfying answer, put forward by no less a statesman of science than Fred Hoyle and later Francis Crick. Life started somewhere else and infected our planet, either by chance or by the machinations of some godlike extraterrestrial intelligence. Perhaps it did. Who would go to the stake to say that it didn't? But most scientists would back away from such reasoning, with good reason. It is tantamount to an assertion that science cannot answer the question before we've even bothered to look into whether science can, in fact, answer it. The usual reason given for seeking salvation elsewhere in the universe is time. There has not been enough time on Earth for the stupefying complexity of life to evolve. But who says? The Nobel laureate Christian de Duve, equally eminent, argues altogether more thrillingly that the determinism of chemistry means that life had to emerge quickly. In essence, he says chemical reactions must happen rapidly or not at all. If any reaction takes a millennium to complete, then the chances are that all the reactants will simply dissipate or break down in the meantime, unless they are continually replenished by other, faster reactions. The origin of life was certainly a matter of chemistry, so the same logic applies. The basic reactions of life must have taken place spontaneously and quickly. So, life, for de Duve, is far more likely to evolve in 10,000 years than 10 billion. We can never know how life really started on Earth. Even if we succeed in producing bacteria or bugs that crawl out from swirling chemicals in a test tube, we will never know if that is how life actually started on our planet, merely that such things are possible, and perhaps more likely than we once thought. But science is not about exceptions, it's about rules, and the rules that govern the emergence of life on our own planet should apply throughout the universe. The quest for the origin of life is not an attempt to reconstruct what happened at 6:30 a.m. on Thursday morning in the year 3,851 million BC, but for the general rules that must govern the emergence of any life anywhere in the universe, and especially on our planet, the only example we know. While the story we'll trace is almost certainly not correct in every particular, it is, I think, broadly plausible. I want to show that the origin of life is not the great mystery it is sometimes made out to be, but that life emerges, perhaps almost inevitably, from the turning of our globe. Science is not just about rules, of course. It's also about the experiments that elucidate the rules. Our story begins in 1953 then, an annus mirabilis marked by the coronation of Queen Elizabeth II, the ascent of Everest, the death of Stalin, the elucidation of DNA, and, not least, the Miller-Urey Experiment, the symbolic origin of life research. Stanley Miller was at that time a headstrong doctoral student in the lab of Nobel laureate Harold Urey. He died, perhaps a touch embittered, in 2007, still fighting for views that he had upheld doubtily for half a century. But whatever the fate of his own particular ideas, Miller's true legacy was the field that he founded on his remarkable experiments, the results of which retain the power to amaze even today. Miller filled a large glass flask with water and a mixture of gases to simulate what he took to be the primordial composition of the Earth's atmosphere. The gases he chose were believed, from spectroscopy, to make up the atmosphere of Jupiter, and were reasonably assumed to have been plentiful on the young Earth too, to wit, ammonia, methane, and hydrogen. Through this mixture, Miller passed electric sparks to simulate lightning, and waited. After a few days, a few weeks, a few months, he took samples and analyzed them to determine exactly what he was cooking, and his findings exceeded even his own wildest imaginings. He was cooking a primordial soup, a near-mythical mix of organic molecules, including a few amino acids, the building blocks of proteins, and probably the most symbolic molecules of life, certainly at that time, before DNA achieved fame. Even more strikingly, the amino acids that actually formed in Miller's soup tended to be the same as those used by life, rather than others drawn randomly from a large reservoir of potential structures. In other words, Miller electrified a simple mixture of gases, and the basic building blocks of life all congealed out of the mix. It was as if they were waiting to be bidden into existence. Suddenly, the origin of life looked easy. The idea must have captured something of the spirit of the age, for the story made the cover of Time magazine, an unprecedented splash of publicity for a scientific experiment. Over time, though, the idea of a primordial soup fell out of favor. Its fortunes hit a nadir when analyses of ancient rocks made it plain that the Earth had never been rich in methane, ammonia, and hydrogen, at least not after the great asteroid bombardment that blasted off the Moon. That colossal bombardment shredded the first atmosphere of our planet, sweeping it away into space. More realistic simulations of the primordial atmosphere proved disappointing. Try passing electric discharges through a mixture of carbon dioxide and nitrogen with trace levels of methane and other gases, and your yield of organic molecules drops dismally. Scarcely an amino acid in sight. The primordial soup became little more than a curiosity, if still a fine demonstration that organic molecules could be made by simple means in the lab. The soup was rescued by the detection of abundant organic molecules in space, most notably on comets and meteorites. A few of these seemed to be composed almost entirely of dirty ice and organic molecules, and served up a remarkably similar array of amino acids to those formed by electrifying gases. Beyond the surprising fact of their existence, it was beginning to look as if there was something specially favored about the molecules of life, a small subset of the vast library of all possible organic molecules. The great asteroid bombardment now took on quite a different face. No longer merely destructive, the pounding became the ultimate source of all the water and organic molecules needed for life to get going. The soup was not indigenous to Earth, but delivered from outer space. And although most organic molecules would have been frazzled on impact, calculations suggested that enough could have survived to stock a soup. If not quite the seeding of life from space advocated by cosmologist Fred Hoyle, the idea nevertheless tied the origins of life, or at least the soup, to the fabric of the universe. Life was no longer a lonely exception, but now a magisterial cosmological constant, inevitable as gravity. Needless to say, astrobiologists loved the idea. Many still do. Quite apart from being a pleasing idea, it gave them job security. The soup was also pleasingly palatable with molecular genetics, and especially the idea that life is all about replicators, in particular genes made of DNA or RNA, which can copy themselves with fidelity and pass on to the next generation. More on this in the next chapter. It is certainly true that natural selection can't work without some sort of replicator, and it is equally true that life can only evolve complexity through the auspices of natural selection. For many molecular biologists, then, the origin of life is the origin of replication, and a soup fits that idea nicely, as it seems to provide all the constituents needed for competing replicators to grow and evolve. In a nice thick soup, the replicators take what they need, forming longer, more complex polymers, and eventually manipulating other molecules into elaborate structures such as proteins and cells. In this view, the soup is an alphabetic C writhing with letters, just waiting for natural selection to fish them out and turn them into surpassing prose. For all this, the soup is a pernicious idea. Not pernicious because it's necessarily wrong. There really might have been a primordial soup once upon a time, even if it was a lot more dilute than originally claimed. It is pernicious because the idea of a soup deflected attention away from the true underpinnings of life for decades. Take a large, sterilized tin of soup or peanut butter and leave it for a few million years. Will life emerge? No. Why not? Because, left to themselves, the contents will do nothing but break down. If you zap the tin repeatedly, you won't be any better off, for the soup will only break down even faster. A sporadic and massive discharge like lightning might persuade a few sticky molecules to congeal together in lumps, but it is far more likely just to shred them into bits again. Could it create a population of sophisticated replicators in a soup? I doubt it. As the Arkansas Traveler has it, you can't get there from here. It's just not thermodynamically reasonable, for the same reasons that a corpse can't be brought back to life by electrocuting it repeatedly. Thermodynamics is one of those words best avoided in a book with any pretense to be popular, but it's more engaging if seen for what it is, the science of desire. The existence of atoms and molecules is dominated by attractions, repulsions, wants, and discharges, to the point that it becomes virtually impossible to write about chemistry without giving in to some sort of randy anthropomorphism. Molecules want to lose or gain electrons, attract opposite charges, repulse similar charges, or cohabit with molecules of similar character. A chemical reaction happens spontaneously if all the molecular partners desire to participate, or they can be pressed to react unwillingly through greater force. And of course some molecules really want to react but find it hard to overcome their innate shyness. A little gentle flirtation might prompt a massive release of lust, a discharge of pure energy. But perhaps I should stop there. My point is that thermodynamics makes the world go round. If two molecules don't want to react together, then they won't be easily persuaded. If they do want to react, they will, even if it takes some time to overcome their shyness. Our lives are driven by wants of this kind. The molecules in food want very much to react with oxygen, but luckily they don't react spontaneously. They're a touch shy, or we'd all go up in flames. But the flame of life, the slow-burning combustion that sustains us all, is a reaction of exactly this type. Hydrogen stripped from food reacts with oxygen to release all the energy we need to live. At bottom, all life is sustained by a main reaction of a similar type, a chemical reaction that wants to happen and releases energy that can be used to power all the side reactions that make up metabolism. All this energy, all our lives, boils down to the juxtaposition of two molecules totally out of equilibrium with each other, hydrogen and oxygen, two opposing bodies that conjoin in blissful molecular union with a copious discharge of energy, leaving nothing but a small, hot puddle of water. And that is the problem with the primordial soup. It is thermodynamically flat. Nothing in the soup particularly wants to react, at least not in the way that hydrogen and oxygen want to react. There is no disequilibrium, no driving force to push life up the very steep energetic hill to the formation of truly complex polymers such as proteins, lipids, polysaccharides, and most especially RNA and DNA. The idea that replicators like RNA were the first figments of life, predating any thermodynamic driving force, is, in Mike Russell's words, like removing the engine from an automobile and expecting the regulating computer to do the driving. But if not from a soup, where did the engine come from? The first clue to an answer came in the early 1970s, when rising plumes of warmish water were noticed along the Galapagos Rift, not far from the Galapagos Islands. Appropriately enough, the islands, whose richness once seeded the origin of species in Darwin's mind, now offered a clue to the origin of life itself. Little happened for a few years. Then, in 1977, 8 years after Neil Armstrong set foot on the moon, the U.S. naval submersible Alvin descended to the rift, seeking the oceanic hydrothermal vents that presumably gave rise to the warm water plumes, and duly found them. Yet, while their existence hardly came as a surprise, the sheer exuberance of life in the Bible-black depths of the rift came as a genuine shock. Here were giant tube worms, some of them 8 feet long, mixed with clams and mussels as big as dinner plates. If giants in the ocean depths were not unusual, just think of the giant squid. Their sheer abundance was astounding. Population densities in the deep-sea vents rival a rainforest or a coral reef, despite being powered by the exhalations of the vents rather than the sun. Perhaps most dramatic of all were the vents themselves, which soon acquired the name black smokers. As it happened, the Galapagos rift vents were tame affairs compared with some of the other 200 vent fields discovered since, scattered along the ocean ridges of the Pacific, Atlantic, and Indian Oceans. Tottering black chimneys, some of them tall as skyscrapers, pump billowing black smoke into the oceans above. The smoke is not real smoke, but broiling metal sulfides invading the seawater, welling up from the magma furnace below, acidic as vinegar, reaching temperatures of 400 degrees centigrade in the crushing pressure of the ocean deep before precipitating in the cold waters. The chimneys themselves are composed of sulfur minerals like iron pyrites, better known as fool's gold, which settle out from the black smoke, amassing in thick deposits over wide areas. Some chimneys grow at startling rates, as much as 30 centimeters in a day, and can tower to 60 meters before crashing down. This bizarre and isolated world seemed to be a vision of hell, and came replete with brimstone and the foul reek of hydrogen sulfide gas emanating from the smokers. Surely only the disturbed mind of Hieronymus Bosch could have imagined the giant tube worms, lacking either a mouth or an anus, and the eyeless shrimp swarming in countless multitudes on the ledges beneath the chimneys, grotesque as a plague of locusts. Life in the smokers doesn't just endure these infernal conditions, it can't live without them. It thrives on them. But how? The answer lies in the disequilibrium. As seawater percolates down to the magma beneath the black smokers, it is superheated and charged with minerals and gases, most notably hydrogen sulfide. Sulfur bacteria can extract hydrogen from this mix and attach it to carbon dioxide to form organic matter. The reaction is the basis of life in the vents, allowing bacteria to flourish with no direct input from the sun. But the conversion of carbon dioxide to organic matter costs energy, and to provide it, the sulfur bacteria need oxygen. The reaction of hydrogen sulfide with oxygen releases the energy that powers the vent world and is equivalent to the reaction of hydrogen with oxygen that powers our own lives. The products are water, as before, but then elemental sulfur, the biblical brimstone that gives the sulfur bacteria their name. It's worth noting that the vent bacteria have no direct use for either the heat or any other aspect of the vent beyond the hydrogen sulfide emitted. This gas is not inherently rich in energy. It is the reaction with oxygen that provides the energy, and this depends on the interface between the vents and the oceans, the juxtaposition of two worlds in dynamic disequilibrium. Only the bacteria living right next to the vents, drawing from both of the worlds simultaneously, can pull off these reactions. The vent animals themselves graze on the bacterial mats, in the case of vent shrimp, or nurture bacteria within themselves, as if tending an internal farm. This explains why, for example, the giant tube worms don't need a digestive tract. They're fed from inside by herds of bacteria. But the strict requirement to provide both hydrogen sulfide and oxygen gives the animal hosts some interesting dilemmas, for they must bring a little of the two worlds together within themselves. Much of the curious anatomy of the tube worms stems from this unyielding obligation. It didn't take long for the conditions in the vent world to register with scientists considering the origin of life. First among them, the oceanographer John Barras at the University of Washington in Seattle. The vents immediately solved many of the problems of the soup, most obviously the problem with thermodynamics. There was nothing of the equilibrium about that black belching smoke. Having said that, the interface between the vents and the oceans would have been rather different on the early Earth, as there was little or no oxygen back then. The driving force could not have been the reaction of hydrogen sulfide with oxygen as in modern respiration. In any case, respiration at the cellular level is a complex process that must have taken time to evolve. It can't have been the primordial energy source. Instead, according to the iconoclastic German chemist and patent attorney Gunther Wechtershauser, that earliest engine of life was the reaction of hydrogen sulfide with iron to form the mineral iron pyrites, a reaction that occurs spontaneously, releasing a modicum of energy that can be captured, at least in principle. Wechtershauser came up with a chemical scheme for the origin of life that looked like nothing else. The energy released by the formation of pyrites is not enough to convert carbon dioxide into organic matter, so Wechtershauser hit on carbon monoxide as a more reactive intermediate. This gas is indeed detected in acid vents. He promoted other sluggish organic reactions with various iron-sulfur minerals which seemed to have outlandish powers of catalysis. And, for an encore, Wechtershauser and his colleagues managed to demonstrate many of these theoretical reactions in the lab, proving them to be more than merely plausible. It was a tour de force that overturned decades-old ideas about how life might have originated, conjuring it up in a hellish environment from the most unexpected of ingredients, essentially hydrogen sulfide, carbon monoxide, and iron pyrites, two poisonous gases and fool's gold. One scientist, on first reading Wechtershauser's work, remarked that it felt like stumbling across a scientific paper that had fallen through a time warp from the end of the 21st century. But is he right? Harsh criticisms have been levelled at Wechtershauser too, in part because he is a genuine revolutionary, overturning long-cherished ideas, in part because his haughty manner tends to exasperate fellow scientists, and in part because there are legitimate misgivings about the picture he paints. Perhaps the most intractable failing is the concentration problem, which also afflicts the idea of a soup. Any organic molecules must dissolve in an ocean of water, and so are highly unlikely to ever meet each other and react to form polymers like RNA and DNA. There is nothing to contain them. Wechtershauser counters that all his reactions can take place on the surface of minerals like iron pyrites. But there is a difficulty with this too, which is that reactions cannot run to completion if the end products are not released from the surface of the catalyst. Everything either gums up or dissipates. Mike Russel, now at the Jet Propulsion Laboratory in Pasadena, proposed a solution to all these problems in the mid-1980s. Russell is a kind of prophetic scientific bard, prone to incantations of geopoetry, and has a view of life rooted in thermodynamics and geochemistry that seems obscure to many biochemists. But over the decades, Russell's ideas have attracted a growing band of supporters who see in his vision a uniquely workable solution to the origin of life. Both Wechtershauser and Russell agree that hydrothermal vents are central to the origin of life. But beyond that, where one sees black, the other sees white. One postulates volcanism, the other its antithesis. One prefers acids, the other alkalis. For two ideas that are sometimes confounded, they have remarkably little in common. Let me explain. The ocean ridges, which host the black smokers, are the source of new, spreading sea floor. From these centres of volcanic activity, the rising magma slowly forces the adjoining tectonic plates apart, the plates creeping away at the speed of growing toenails. As these inching plates collide with each other, far away, one plate is forced to plunge beneath another, while the other is thrust into petrified convulsions. The Himalayas, the Andes, the Alps, all were thrown into relief by the collision of tectonic plates in this way. But the slow movement of fresh crust across the sea floor also exposes new rocks derived from the mantle, the layer beneath the crust. Such rocks give rise to a second type of hydrothermal vent, very different to the black smokers, and it is this type of vent that Russel himself champions. This second type of vent is not volcanic, and there's no magma involved. Instead, it depends on the reaction of these freshly exposed rocks with seawater. Water doesn't just percolate into such rocks, it physically reacts with them. It is incorporated into them, altering their structure to form hydroxide minerals like serpentine, named after its resemblance to the mottled green scales of a serpent. The reaction with seawater expands the rock, causing it to crack and fracture, which in turn permits further seawater to penetrate, perpetuating the process. The scale of such reactions is astonishing. The volume of water bound into rock in this way is believed to equal the volume of the oceans themselves. As the ocean floor spreads, these expanded, hydrated rocks ultimately plunge beneath a colliding plate, where they are superheated again in the mantle. Now they give up their water, releasing it into the bowels of the earth. This contamination with seawater drives the convective circulation deep in the mantle, forcing magma back up to the surface at the mid-ocean ridges and volcanoes. And so, the turbulent volcanism of our planet is largely driven by a continuous flux of seawater through the mantle. It's what keeps our world out of equilibrium. It is the turning of our globe. But the reaction of seawater with mantle-derived rocks does more than just drive the relentless volcanism of our planet. It also releases energy as heat, along with copious quantities of gases like hydrogen. In fact, the reaction transfigures everything dissolved in seawater as if it were a magic distorting mirror, reflecting back grotesquely swollen images in which all the reactants are loaded up with electrons. Technically, they're said to be reduced. The main gas emanating is hydrogen, simply because seawater is mostly water. But there are small amounts of various other gases, reminiscent of Stanley Miller's mixture, so useful for generating the precursors of complex molecules like proteins and DNA. Thus, carbon dioxide is transformed into methane, nitrogen returns as ammonia, and sulfate belches back as hydrogen sulfide. The heat and gases make their way back to the surface, where they break through as the second type of hydrothermal vent. These differ in virtually every detail from black smokers. Far from being acidic, they tend to be quite strongly alkaline. Their temperature is warm or hot, but well below the superheated fury of black smokers. They are usually found some way away from the mid-ocean ridges, the source of fresh spreading sea floor. And rather than forming vertical black chimneys with a single orifice through which black smoke billows, they tend to form complex structures riddled with tiny bubbles and compartments which precipitate as the warm alkaline hydrothermal fluids percolate into the cold ocean waters above. I suspect the reason that only a few people have ever heard of this type of vent relates to the off-putting term serpentinization, again from the mineral serpentine. For our purposes, let's simply label them alkaline vents, even if this might sound a bit limp compared with the virility of black smokers. We'll see the full significance of the word alkaline later. Curiously, until recently, alkaline vents were predicted in principle, but only known from a few fossil deposits. The most famous, at Tina in Ireland, is about 350 million years old, and set Mike Russel thinking back in the 1980s. When he examined thin sections of the bubbly rocks from near the fossil vent under an electron microscope, he found the tiny compartments were a similar size to organic cells, 1/10 of a millimeter or less in diameter, and interconnected in labyrinthine networks. He postulated that similar mineral cells could be formed when alkaline vent fluids mingled with acidic ocean waters, and soon succeeded in producing porous, rocky structures in the lab by mixing alkalis with acids. In a Nature letter in 1988, Russel noted that alkaline vent conditions should have made them an ideal hatchery for life. The compartments provided a natural means of concentrating organic molecules, while their walls, composed of iron-sulfur minerals such as macinawhite, endowed these mineral cells with the catalytic properties envisaged by Günther Wechtershauser. In a 1994 paper, Russel and his colleagues proposed that life emerged from growing aggregates of iron sulfide bubbles containing alkaline and highly reduced hydrothermal solution. These bubbles were inflated hydrostatically at sulfidic submarine hot springs sited some distance from the oceanic spreading centers 4 billion years ago. The words were visionary, for at the time such a living deep-sea alkaline vent system had never been discovered. Then, at the turn of the millennium, scientists aboard the submersible Atlantis stumbled across exactly this kind of vent around 15 kilometers from the mid-Atlantic ridge on an underwater mountain that also happened to be called the Atlantis Massif. Inevitably named Lost City after the mythic metropolis, its delicate white pillars and fingers of carbonate reaching up into the inky blackness made the name eerily appropriate. The vent field was unlike any other yet discovered. Some of the chimneys were as tall as the black smokers, the largest, dubbed Poseidon, standing 60 meters proud. But far from being stolidly robust structures, these delicate fingers were ornate as Gothic architecture, full of vacuous doodles, in John Julius Norwich's words. Here the hydrothermal exhalations were colourless, giving the impression that the city had been suddenly deserted and preserved for all time in its intricate Gothic splendour. No hellhole of black smokers, these were delicate white non-smokers, their petrified fingers reaching for heaven. Invisible they may be, but the exhalations are real enough and sufficient to support a living city. The chimneys are not composed of iron-sulfur minerals. Hardly any iron dissolves in oxygen-rich oceans. Russell's predictions relate to much earlier times. But their structure is still porous, a maze of microscopic compartments with feathery aragonite walls. Curiously, the old structures that have fallen silent, no longer bubbling with hydrothermal fluids, are far more solid, their pores clogged up with calcite. In contrast, the living vents really are alive, the pores a hive of industrious bacterial activity in which the chemical disequilibrium is exploited to the full. Animals there are too, rivaling the black smokers in diversity, but falling far short in terms of sheer size. The reason appears to be a matter of ecology. The sulfur bacteria thriving in the black smokers readily adapt to life in their animal hosts, while the bacteria, or strictly archaea, found in the lost city don't form such partnerships. Lacking internal farms, the vent animals grow less efficiently. Life in the lost city is built on the reaction of hydrogen with carbon dioxide, which is actually the basis of all life on our planet. In the lost city, unusually, the reaction is direct, while in practically all other cases it is indirect. Raw hydrogen, bubbling from the ground as a gas, is a rare gift on our planet, and life is normally obliged to seek out occult supplies, bound in tight molecular grip to other atoms, as in water or hydrogen sulfide. To rip hydrogen from such molecules and bind it onto carbon dioxide costs energy that comes ultimately from the sun in photosynthesis or from exploiting chemical disequilibria in the vent world. Only in the case of hydrogen gas itself does the reaction take place spontaneously, if painfully slowly. But from a thermodynamic point of view, the reaction is a free lunch that you are paid to eat, in Everett Schock's memorable phrase. In other words, the reaction generates organic molecules directly and at once releases a substantial amount of energy that can, in principle, be used to power other organic reactions. So Russell's alkaline vents fit the bill as a hatchery of life. They are an integral part of a system that turns over the surface of the globe, promoting the restless volcanism of our planet. They are perpetually out of equilibrium with the oceans, bubbling a steady supply of hydrogen that reacts with carbon dioxide to form organic molecules. They form a labyrinth of porous compartments which retain and concentrate any organic molecules formed, making the assembly of polymers, like RNA, far more likely, as we'll see in the next chapter. They are long-lived. The lost city chimneys have now been venting for 40,000 years, 2 orders of magnitude longer than most black smokers. And they were more plentiful on the early Earth, when the cooling mantle interfaced more directly with the oceans. In those days, too, the oceans were loaded with dissolved iron, and the micro-compartments would have had catalytic walls composed of iron-sulfur minerals like the fossil vents at Tina in Ireland. They would have worked, in fact, as natural flow reactors, with thermal and electrochemical gradients circulating reactive fluids through catalytic compartments. That is all very well, but a single reactor, however valuable, scarcely constitutes life. How did life progress from such natural reactors to the complex, marvelous tapestry of invention and ingenuity that we see around us? The answer, of course, is unknown, but there are clues that derive from the properties of life itself, and in particular from an inner core of deeply conserved reactions common to almost all life on Earth today. This core of metabolism, a living inner fossil, preserves echoes of the most distant past, echoes that are consonant with primordial origins in an alkaline hydrothermal vent. There are 2 ways of approaching the origin of life, the bottom-up and the top-down. So far, in this chapter, we have taken the bottom-up approach, considering the geochemical conditions and thermodynamic gradients that most likely existed on the early Earth. We have come up with warm deep-sea hydrothermal vents, bubbling hydrogen gas into an ocean saturated with carbon dioxide as the most likely setting for the origin of life. Natural electrochemical reactors would have been capable of generating both organic molecules and energy, but we haven't considered yet exactly what reactions are likely to have taken place or how they led to life as we know it. The only true guide to how life came to be is life as we know it today, that is to say, the top-down approach. We can catalogue the properties shared by all living things to reconstruct the hypothetical properties of a last universal common ancestor, known fondly as LUCA. So, for example, because only a small subset of bacteria is capable of photosynthesis, it is unlikely that LUCA herself was photosynthetic. If she were, then the great majority of her descendants must have abandoned a valuable skill which seems at best improbable, even if it can't be excluded with certainty. Conversely, all life on Earth shares common properties. All living things are composed of cells, excluding viruses which can only operate within cells. All have genes made of DNA. All encode proteins by way of a universal code for particular amino acids. And all living things share a common energy currency known as ATP, adenosine triphosphate, which functions as a sort of 10-pound note, capable of paying for all kinds of work about the cell. More on this later. We can infer reasonably that all living organisms inherited their shared properties from that remote common ancestor, LUCA. All life today also shares a common core of metabolic reactions, at the heart of which is a little cycle of reactions known as the Krebs Cycle, after Sir Hans Krebs, the German Nobel laureate who first elucidated the cycle in Sheffield in the 1930s after fleeing the Nazis. The Krebs cycle occupies hallowed ground in biochemistry, but for generations of students it felt like the worst kind of dusty ancient history to be rote-learned in time for exams and then forgotten. Yet there is something iconic about the Krebs cycle. Pinned to the walls of cluttered offices in biochemistry departments, the kind of office where you'll find piles of books and papers on the desk spilling over onto the floor and into the bin unemptied for a decade, you'll often find a faded, curling, dog-eared metabolic chart. You peer at it with a mixture of fascination and horror while you wait for the professor to return. They are shocking in their complexity, like a lunatic's version of an underground tube map with little arrows running in all directions, looping back round on each other. Although faded, you can just make out that these arrows are all color-coded for different pathways, proteins in red, lipids in green, and so on. Down towards the bottom, somehow giving the impression that it is at the center of this insurrection of arrows, is a tight little circle, maybe the only circle, indeed the only ordered bit on the whole map. That's it, the Krebs cycle. And as you peer at it, you begin to appreciate that virtually all the other arrows on the map somehow spin off from the Krebs cycle, like the spokes of a mangled wheel. It is the center of everything, the metabolic core of the cell. The Krebs cycle doesn't feel so dusty anymore. Recent medical research has shown it to stand at the heart of the cell's physiology as well as its biochemistry. Changes in the rate at which the cycle spins affect everything from aging to cancer to energy status. But what came as an even bigger surprise is that the Krebs cycle can go backwards. Normally, the cycle consumes organic molecules from food and spins off hydrogen, destined for burning with oxygen in respiration, and carbon dioxide. The cycle therefore not only provides precursors for metabolic pathways, it also serves up the little packets of hydrogen needed for generating energy as ATP. In reverse, the Krebs cycle does the opposite. It sucks in carbon dioxide and hydrogen to form new organic molecules, all the basic building blocks of life. And instead of releasing energy as it spins, the reverse cycle consumes ATP. Provide it with ATP, carbon dioxide, and hydrogen, and the cycle spins out the basic building blocks of life, as if by magic. This reverse spinning of the Krebs cycle is not widespread, even in bacteria, but it is relatively common in the bacteria that live in hydrothermal vents. It is plainly an important, if primitive, way of converting carbon dioxide into the building blocks of life. The pioneering Yale biochemist Harold Morowitz, now at the Krasnow Institute for Advanced Study, Fairfax, Virginia, has been teasing out the properties of the reverse Krebs cycle for some years. In broad terms, his conclusion is that given sufficient concentrations of all the ingredients, the cycle will spin on its own. It is bucket chemistry. If the concentration of one intermediate builds up, it will tend to convert into the next intermediate in succession. Of all possible organic molecules, those of the Krebs cycle are the most stable and so the most likely to form. In other words, the Krebs cycle was not invented by genes. It is a matter of probabilistic chemistry and thermodynamics. When genes evolved later on, they conducted a score that already existed, just as the conductor of an orchestra is responsible for the interpretation, the tempo, and the subtleties, but not the music itself. The music was there all along, the music of the spheres. Once the Krebs cycle was spinning and provided with a source of energy, side reactions would have been almost inevitable, giving rise to more complex precursors such as amino acids and nucleotides. How much of the core metabolism of life on Earth arises spontaneously, and how much is a later product of genes and proteins, is an interesting question, and one that is beyond the scope of a book like this. But I would like to make one general point. The great majority of attempts to synthesize the building blocks of life have been too purist. They start with simple molecules like cyanide, which have nothing to do with the chemistry of life as we know it. In fact, they are anathema to it. Then attempt to synthesize the building blocks of life by playing around with factors like the pressure, temperature, or electrical discharges, totally unbiological parameters, all of them. But what happens when you start out with the molecules of the Krebs cycle and some ATP, ideally in an electrochemical reactor like that proposed by Mike Russel? Just how much of our dog-eared metabolic chart arises spontaneously from these ingredients in a kind of ethereal cast that gradually fills up from the bottom with the thermodynamically most likely molecules? I am not alone in suspecting quite a lot of it, perhaps up to the level of small proteins, strictly polypeptides, and RNA, at which point natural selection begins to take over. All this is a matter of experimentation, and these experiments are mostly yet to be done. For any of it to be realistic, we need a nice steady production of that magic ingredient ATP, and on that score you may well feel that we're getting ahead of ourselves, trying to run before we've learnt to walk. How do we generate ATP? The answer I find most persuasive comes from the brilliant, if frequently outspoken, American biochemist Bill Martin, who forsook the U.S. to take a job as professor of botany at the University of Dusseldorf. From here, Martin has been the source of a steady flow of iconoclastic ideas about the origin of almost everything that matters in biology. Some of it may be wrong, but he is always thrilling and nearly always makes one see biology from a different point of view. A few years ago, Martin sat down with Mike Russel, and the pair of them attacked the transition from geochemistry to biochemistry. Since then, the insights have been flowing free. Let's take the ride. Martin and Russel went back to basics, the flow of carbon into the organic world. Today, they note, there are only 5 metabolic pathways by which plants and bacteria incorporate hydrogen and carbon dioxide into the living world to generate organic matter, one of which is the reverse Krebs cycle, as we've seen. 4 of the 5 pathways consume ATP, as does the Krebs cycle, and so can only take place with an input of energy. Yet the 5th pathway, the straight reaction of hydrogen with carbon dioxide, not only produces organic molecules, but it also releases energy. 2 groups of ancient organisms do exactly this via a series of broadly similar steps, and one of these 2 groups we've already met, the archaea that thrive in the lost city vent field. If Martin and Russel are right, the remote ancestors of these archaea were performing the same set of reactions in an almost identical environment 4,000 million years ago at the dawn of life. But the reaction of hydrogen with carbon dioxide is not quite as straightforward as it sounds, for the 2 molecules don't react spontaneously. They are rather shy and need to be persuaded to dance by a catalyst. And they also need a small input of energy to get things going. Only then do the 2 conjoin, releasing rather more energy as they do so. The catalyst is simple enough. The enzymes that catalyze the reaction today contain little clusters of iron, nickel, and sulfur at their cores, with a structure very similar to a mineral found in vents. This suggests that the primordial cells simply incorporated a ready-made catalyst, a feature that points to the great antiquity of the pathway, as it does not entail the evolution of sophisticated proteins. As Martin and Russel put it, the pathway has rocky roots. The source of energy needed to get the ball rolling in the vent world, at least, turns out to be the vents themselves. An unexpected reaction product betrays their hand. A reactive form of vinegar known as acetyl thioester. Acetyl thioesters form because carbon dioxide is quite stable and resists attack by hydrogen, but is vulnerable to more reactive free radical fragments of carbon or sulfur found in vents. In effect, the energy needed to persuade carbon dioxide to react with hydrogen comes from the vents themselves in the form of reactive free radicals, and these give rise to the acetyl thioesters. Acetyl thioesters are significant because they stand at an ancient branch point in metabolism still found in organisms today. When carbon dioxide reacts with an acetyl thioester, we take a branch leading to the formation of more complex organic molecules. The reaction occurs spontaneously and releases energy to produce a 3-carbon molecule called pyruvate, a name that ought to make biochemists sit up and blink, for it is an entry point into the Krebs cycle. In other words, a few simple reactions, all thermodynamically favorable and several catalyzed by enzymes with mineral-like clusters at their core, giving them rocky roots, take us straight to the metabolic heart of life, the Krebs cycle, without any more ado. And once we've broken into the Krebs cycle, all we need is a nice, steady supply of ATP to start it spinning, to generate the building blocks of life. Energy is exactly what the other prong of the fork provides when phosphate reacts with another acetyl thioester. Admittedly, the reaction doesn't produce ATP, but a simpler form called acetyl phosphate. Even so, this serves much the same purpose and is still used alongside ATP by some bacteria today. It does exactly the same thing as ATP. It transfers its reactive phosphate group onto other molecules, giving them a kind of energy tag that activates them in turn. The process is a bit like the children's game of tag, in which one child is it and must touch a second child who then becomes it instead. The child who is it gains a reactivity to pass on to the next child. Transferring phosphate from one molecule to another works in much the same way. The reactive tag activates molecules that would not otherwise react. This is how ATP can drive the Krebs cycle backwards, and acetyl phosphate does exactly the same thing. Once the reactive phosphate tag has been transferred, the waste is simply vinegar, a common product of bacteria today. Next time you open a bottle of wine that has gone sour, turning to vinegar, spare a thought for the bacteria at work in the bottle, generating a waste product as old as life itself, a waste more venerable than even the finest vintage. Pulling all this together, alkaline hydrothermal vents continuously generate acetyl thioesters, providing both a starting point for forming more complex organic molecules and the energy needed to make them, packaged in a format essentially the same as that used by cells today. The mineral cells that riddle the chimneys provide at once the means of concentrating the products, favoring such reactions, and the catalysts needed to speed up the process without any requirement for complex proteins at this stage. And finally, the bubbling of hydrogen and other gases into the labyrinth of mineral cells means that all the raw materials are replenished continually and thoroughly mixed. It is truly a fountain of life, except for one niggling little detail with the most pervasive consequences. The problem relates to that little kick of energy that's needed up front to warm relations between hydrogen and carbon dioxide. I mentioned that it's not a problem in the vents themselves, as the hydrothermal conditions form reactive free radicals that get the ball rolling. But it is a problem for free-living cells that don't live in vents. Instead, they need to spend ATP to get things going, like buying a drink to break the ice on a first date. What's the problem with that? It's a matter of accountancy. The reaction of hydrogen with carbon dioxide releases enough energy to generate one molecule of ATP. But if you must spend one ATP to generate one ATP, then there's no net gain. And if there's no net gain, there can't be any spinning of the Krebs cycle, no production of complex organic molecules. Life might be able to get going in the vents, but then should remain forever bound to the vents by a kind of thermodynamic umbilical cord that could never be cut. Obviously, life isn't tied to the vents. If this whole account is not pure make-believe, how did we escape? The answer, put forward by Martin and Russel, is marvelous, for it explains why almost all life today makes use of an utterly peculiar method of respiration to generate energy, perhaps the most confoundingly counterintuitive mechanism in all biology. In The Hitchhiker's Guide to the Galaxy, the hopelessly inept ancestors of modern humans crash onto planet Earth and supplant the resident ape-men. They form a subcommittee to reinvent the wheel and adopt the leaf as legal tender, making everyone enormously rich. But they run into a serious problem with inflation, in which it costs about 3 deciduous forests to pay for a single ship's peanut. So our ancestors embark on a massive deflation program and burn down all the forests. It all sounds horribly plausible. Sinking beneath the frivolity, there is, I suppose, a serious point about the nature of currency. There is nothing whatsoever to anchor value. A peanut could be worth a gold bar, 1 penny, or 3 deciduous forests. It all depends on relative valuation, rarity, and so on. A £10 note can be worth whatever it wants to be. But this is not the case in chemistry. Earlier on, I compared ATP to a £10 note, and I chose the value with care. The bond energies in ATP are such that you must spend £10 to make 1 ATP, and you receive exactly £10 when you spend it. It is not relative in the same way as human currency, and that's the root of the problem for any bacteria that try to leave the vents. ATP is not so much a universal currency as a universal £10 note, inflexible in value, and with no such thing as small change. If you want to buy a cheap drink to break the ice on a first date, you must hand over your £10 note, and even if the drink costs £2, you still don't get any change. There is no such thing as a fifth of an ATP molecule. And when you capture the energy released by the reaction of hydrogen with carbon dioxide, you can only store it in units of £10. Let's say you could, in principle, gain £18 from the reaction. That's not sufficient to make 2 ATPs, so you must make only 1. You lose £8 because there is no such thing as small change. Most of us face the same irritating problem at bureaux de change, which only deal in large denominations. Overall, then, despite needing to spend £2 to get things going, with a payback of £18 when forced to use our universal £10 note, we must spend £10 to gain £10. Bacteria can't avoid this equation. None can grow by the straight reaction of hydrogen with carbon dioxide using ATP alone. And yet they do grow, by way of an ingenious method of breaking up the £10 note into small change, a method known by the formidable name of chemiosmosis, which earned its prime expositor, the eccentric British biochemist Peter Mitchell, the Nobel Prize in 1978. The award finally drew to a close decades of bitter disputes. Today, though, with the perspective of another millennium, we can see that Mitchell's discovery ranks among the most significant of the 20th century. But even those few researchers who long upheld the importance of chemiosmosis struggle to explain why such a strange mechanism should be ubiquitous in life. Like the universal genetic code, the Krebs cycle, and ATP, chemiosmosis is universal to all life and appears to have been a property of the last universal common ancestor, Luca. Martin and Russell explain why. In the broadest of terms, chemiosmosis is the movement of protons over a membrane, hence the resemblance in name to osmosis, the movement of water over a membrane. In respiration, what happens is this. Electrons are stripped from food and passed along a chain of carriers to oxygen. The energy released at several points is used to pump protons across a membrane. The outcome is a proton gradient over the membrane. The membrane acts a bit like a hydroelectric dam. Just as water flowing down from a hilltop reservoir drives a turbine to generate electricity, so in cells the flow of protons through protein turbines in the membrane drives the synthesis of ATP. This mechanism was totally unexpected. Instead of having a nice straightforward reaction between two molecules, a strange gradient of protons is interpolated in the middle. Chemists are used to working with whole numbers. It's not possible for one molecule to react with half of another molecule. Perhaps the most confounding aspect of chemiosmosis is that fractions of whole numbers abound. How many electrons need to be transferred to produce one ATP? Somewhere between 8 and 9. How many protons? The most accurate estimate yet is 4.33. Such numbers made no sense at all until the intermediary of a gradient was appreciated. A gradient, after all, is composed of a million gradations. It doesn't break into whole numbers. And the great advantage of a gradient is that a single reaction can be repeated again and again just to generate one single ATP molecule. If one particular reaction releases 1/100th of the energy needed to generate one ATP, the reaction is simply repeated 100 times, building up the gradient step by step until the proton reservoir is big enough to generate a single ATP. Suddenly, the cell can save up. It has a pocket full of small change. What does all this mean? Let's go back to the reaction of hydrogen with carbon dioxide. It still costs bacteria 1 ATP to get the ball rolling, but they are now able to generate more than 1 ATP as they can save up towards a second ATP. Not a good living, perhaps, but an honest one. More to the point, it makes the difference between the possibility of growth and no possibility of growth. If Martin and Russell are right, and the earliest forms of life grew from this reaction, then the only way life could leave the deep-sea vents was by chemiosmosis. It's certainly true that the only forms of life that live from this reaction today both depend on chemiosmosis and can't grow without it. And it's equally true that almost all life on Earth shares this same curious mechanism, even though it's not always needed. Why? I imagine simply because they inherited it from a common ancestor that couldn't live without it. But here is the chief reason to think Martin and Russell are right: the use of protons. Why not, for example, charged sodium, potassium, or calcium atoms, which are used by our own nervous systems? There's no obvious reason why protons should be preferred to a gradient of any other type of electrically charged particle, and there are some bacteria that generate a sodium gradient rather than a proton gradient, albeit rarely. The main reason, I think, goes back to the properties of Russell's vents. Recall that the vents bubble alkaline fluids into an ocean that is made acidic by dissolved carbon dioxide. Acids are defined in terms of protons. An acid is rich in protons, an alkali poor. So bubbling alkaline fluids into acidic oceans produces a natural proton gradient. In other words, the mineral cells in Russell's alkaline vents are naturally chemiosmotic. Russell himself pointed this out many years ago, but the realization that bacteria simply could not leave the vents without chemiosmosis was one of the fruits of his collaboration with Martin, who looked into the energetics of microbes. And so these electrochemical reactors not only generate organic molecules and ATP, they even handed over an escape plan, the way to evade the universal 10-pound note problem. Of course, a natural proton gradient is only of use if life is able to harness the gradient and later on generate its own gradient. While it's certainly easier to harness a pre-existing gradient than it is to generate something from scratch, neither is straightforward. These mechanisms evolved by natural selection, there is no doubt. Today, it requires numerous proteins specified by genes, and there is no reason to suppose that such a complex system could have evolved in the first place without proteins and genes composed of DNA. And so, we have an interesting loop. Life could not leave the vents until it had learnt how to harness its own chemiosmotic gradient, but it could only harness its own gradient using genes and DNA. It seems inescapable. Life must have evolved a surprising degree of sophistication in its rocky hatchery. This paints an extraordinary portrait of the last common ancestor of all life on Earth. If Martin and Russell are right, and I think they are, she was not a free-living cell, but a rocky labyrinth of mineral cells lined with catalytic walls composed of iron, sulfur, and nickel, and energized by natural proton gradients. The first life was a porous rock that generated complex molecules and energy right up to the formation of proteins and DNA itself. And that means we have only followed half the story in this chapter. In the next, we'll consider the other half, the invention of that most iconic of all molecules, the stuff of genes, DNA.